And as usual, I will start presenting myself. Well, I started with experimental plasma physics because at the time I read somewhere that the plasma physics would soon have abundant and cheap energy. It seems that this is still the promise today. So I changed to something simpler in my master's degree. I want to study pattern formation, perhaps the origin of life, based on Navier-Stokes equations. But it was still very boring to program the numerical resolution of the Navier-Stokes equations in Fortran at that time. Then, looking for something simpler, I was to mechanical statistics, and I was seeking to understand the emergence of intelligence and consciousness from neural network. In my doctorate, I studied replica theory and spin glasses. This same topic earned to Giorgio Paris the Nobel Prize in Physics in 2021 for his contribution to the study of frustrated systems. So I missed again this opportunity. So I moved on. And during my postdoc years, the term complex system was well established as a promising trend. So I went to Max Planck Institute for the Physics of Complex Systems in Dresden and to the Theoretical Physics and Complex System group at the University of Oldenburg, again with pattern formation stuff. And since then, I have been involved with nonlinear dynamics, multifractals, agent-based models, evolutionary algorithms, data mining, deep learning, and so on. And my students have applied all of these to biological, social, economic, political, public safety problems. So, very interdisciplinary. So, from this point, I have some tip for the students. That is, looking back, it's always easier to see a coherent trajectory rather than when the most important career decisions are made. So keep walking, that one day your trajectory will make sense. So said that, I am back to the talk. So I'm going to talk about the structure and the robustness of Sao Paulo public transport network. Yes, this today was a good start to talk about public transportation network. So this is a joint work with Sandro Souza, that was my master student some years ago, and Alison Gonzalez, that is at the moment a student from Fernando Ferreira. So this is our paper that is in the review process just now. Okay, so public transport networks, PTN for a short, are constantly experiencing interruptions, as we saw today in the metro. So there are unintended mechanical failures, and there are also intended attacks. Those events can cause large-scale impact to the city, resulting on delay, financial losses, and even life-threatening situations. So it's an important topic per se. The stability of the public transport network is vital as it plays an important role in the city dynamics and mobility flows. Finding the most important and vulnerable elements in the public transport network is a way to establish a more efficient and reliable system. Robustness, in this sense, in this context, is understood as the ability of the public transport network to absorb disturbances to the nodes, stops and stations, or to the links, bus, subway and train lines, and continue operating closely to the normal conditions. So today I was coming here, and the metro to Barra Funda was interdicted. I jumped in Luz station. I was to the train line number 4 and arrived to the same point. So this is a kind of robustness. You can go around the interruptions. Okay. PTN in big cities are a combination of 3 other networks: buses, subway, and urban trains, frequently managed by different agencies. The Sao Paulo metropolitan area, so how big is the problem? Huh? The Sao Paulo metropolitan area is the 5th largest urban agglomeration in the world, with more than 21 million inhabitants. The Sao Paulo city alone has more than 12 million in 2020. So the Sao Paulo PTN has circa of 1,300 bus lines, 11 subway and train lines, with 153 stations. It's not as big as other cities in the world, but the population it serves is huge. The impact of an interruption in the transportation system can be severe, as nearly half of the population living in the area relies on the PTN for daily commuting. So there is, this is not a new topic, so there is some papers in the literature. I missed the references here, so if you are interested, I can show later. So for instance, the PTN of Berlin, Düsseldorf, and Paris showed scale-free property. 22 PTNs in Poland showed small order behavior for the degree distribution of stops following a power law or exponential function according to the approach chosen for the space representation. So this is the first problem. You have the real network, transportation network, and I do a map to a space representation, a different space representation, and work in this space. Beijing and Chengdu in China showed power law for the degree distribution of stops. But on a larger study in China with 330 cities, using a different representation that is called transfer space. I'm not going in detail here. I'm going to use a different representation here. The degree distribution of stop was described as an exponential function. So as usual, it's very hard to distinguish between exponential function and power law functions, or even log normal functions, depending on the data. So we had the same problem here. So the goal of this paper is to study the Sao Paulo public transport network as a coupled system of bus and rails, meaning subway and trains, by a network-based characterization of its statistical properties. We first show a procedure to create the connected network of bus stops and subway train stations. So this is the first thing to note. The public transport network of Sao Paulo is a combination of bus, train, and metro. And this combination is not completely connected, so it has several clusters. So the first thing that we tried to do was to transform that 3 separate networks in one network that could be percolated completely. So we will first show how we did that. So how we did that? As the PTN is disconnected set of networks, a distance radius around each node is used to group nearby stops and stations. So if you arrive to a station, and you need to change to another line, you are willing to walk maybe 100 meters, maybe 200 meters. And when I do that, I connect these separate networks. So it's a kind of, I mean, in general, we prefer to have systems that are perfectly defined without individuals' decisions. But here is absolutely crucial to consider that willingness to change the networks. Because as you see, the network completely changes its structures. So this distance may be a proxy for users' willingness to move to nearby stops and stations to gain access to transportation. Attacks are simulated, aiming stops, stations, and lines to measure the system's ability to keep connecting destinations in face of ruptures. So we start with an empirical analysis. So the PTN of Sao Paulo is investigated as a coupled network of bus, subway, and train stops. The three networks are interconnected. We made no distinction between them. So we deal with the three networks in the same way. The stations, terminals, and stops are represented as nodes, and their lines and the routes as links. This approach is known as L-space. A node is a stop, and any two stations served successively by a line are connected by a link. The outcome of this representation is a network similar to the real system, preserving stops distributions in the city area and making possible to look at general aspects such as topology, connectivity, finding hubs, clusters, and elements that could cause large damage to the system removals. The data came from the public traffic data is extracted from a local agency called SP Trans, and it follows the general transit feed specification format. So the same algorithms that we developed here can be applied almost immediately for any other PTN in the world. It's very common, this format. So the format allows traffic agencies to publish their data on common global standard, making it easier to reproduce the steps in this study in any city using it. The method described in the previous slides to create the representation of the physical PTN results on a network with 11 disconnected components. So the Sao Paulo public transport networks is a set of networks with 11 completely disconnected components. So how we put this together, or how people put this together? So this is our starting point, our analysis, 11 disconnected components. So here we have a representation. In the top row, you see the original L representation of the bus, train, and subway. Okay, so if people are not willing to walk, the bottom row, we have exactly the same network. But if the people are willing to walk 50 or 100 meters, I'm shut down the units here, so for simplicity. So what happens is that, for instance, these two nodes, may be a bus or a metro, and the metro, will be represented by a unique node. So this network here would be more connected from this in relation to this one, and we will have less links and less nodes. More the people walk, simpler is the network. Okay, so here goes the algorithm. To make the network a complete connected component, an algorithm was developed to group nearby stops into a single one. The idea is to group stops inside a given distance radius ρ into a single node in the network. The radius ρ assumes a range that goes from 0 to 200 meters. Each value of ρ results in a unique network with nodes and links changing as function of stops being grouped. So here is again the general schema. And okay, so the network is created as the metrics are computed for each value of ρ. So we will calculate several complex network metrics, and evaluate it in function of ρ, ranging from 0 to 200 meters in the interval of 5 meters. We have 41 different graphs. And statistical properties are given for each singular network. So, okay, for sure. Previous one.
You said you have 11 disconnected components, but you have connections there. So
Yeah. Look, the public transport network of Sao Paulo has around 20,000 nodes. So here we have just a sketch to give the idea how to collapse. No. This is just for explain the procedure. We have 20,000 nodes in the original network, so it's a huge one. Yeah. No. Okay. So this different distance can be useful as a proxy of passengers' willingness to walk to a nearby stop within a given radius. So this may be an important information for public planning. How much people are willing to walk? In a hot day, they will walk less. In a rain day, also. So this is an option from the user, and this is determining the properties of our network. Okay. As the radius grows, the availability of lines and stops increases, which can result on a larger number of destinations and options to reach the desired location. I mean, the number of stops and links get smaller, but the options to the traveler is higher because now he can access different nodes, isolated previous components. So, okay, of course.
Yeah, I got confused. How do you compute? How do you manage each node to its?
How I compute the nodes?
How do you organize which nodes can be collapsed?
Okay. Okay. So, okay. So, okay. The question is the following: how I organize the nodes so I can choose which one I will collapse? Something like that. Okay. So, this story is quite longer, and I just didn't tell everything. The database is something very peculiar. So we have a bus number. You have the number identification of a particular bus. And then you have the timestamp where the bus was, for instance, 6 o'clock in the morning. And then someone take notes where it is, the time where the the time it arrives to the next node, and so on. So a few lines were automated in the 5 years ago. So the first job is to use this math, because there are a lot of errors. Excuse me? Yeah, there is a lot of errors in this annotation because it was made mainly by humans. So first step is to clean everything. And every node, every bus station, every metro stop has a geographic coordinates. So I know exactly where each node is in Sao Paulo city. So I pick each, for a given row, for instance, 50 meters. I look for each node to see if there are another node in this region, and if there are, I collapse these nodes in a single one. That's the idea. I also delete the links between these nodes that were collapsed. And I do that for all the nodes every time that, so I don't know if I explain.
Because I imagine the central part of São Paulo, you have thousands of bus stops and
Yeah.
train stations.
Okay.
I will repeat the question.
Okay.
So
Thank you.
I imagine in the central part of São Paulo, we have thousands or hundreds of bus stops and train stations,
Yeah.
all within a certain radius of 200 to 200 meters, let's say that. They all get collapsed to the same area.
Same nodes. Yeah.
Yeah.
That's the idea.
So maybe, let's say one node, the radios are combined, let's say, like that.
Look, the original network has a lot of nodes, but the bus stops and the stations that are very close. But in the original mapping, these are disjointed networks. Yeah.
I think I know what the question is. Suppose you have 3 nodes,
3 nodes.
yeah, that are separated by 40 meters.
Yeah.
So node A, B, and C. So A and C would not be connected. So
But
will
A,
you
B-
connect B to A or to C?
That's right.
Yeah, so you have to choose. You make
Yeah,
a choice at some point.
And indeed, we choose. Okay. Well, I'm not sure if I can answer that today because this
No,
is an
yeah.
old job.
No, it's okay. You
Yeah,
just
but
go on.
it's
We can
but
return to
probably
that, yeah.
probably we ran it one time. The algorithm collapsed some nodes and C was out, and then the next time for 51 meters or 52, it get collapsed. So that's the idea. Okay, sorry for the confusion. Thank you. Okay, so we had all that complex network statistics. So let's take a look in each one. So the group and algorithm induces significant structural transformations within the PTN as the radius is extended. This is the point to make here. The transport network is different in each day of the week. If it rains, if it's too hot, if it's a weekend. So to the public authorities to plan a good system, you need to know how much people you walk that day. Do you see? So this is a relevance because you see that the structure will change. So the number of nodes in the network, it goes from nearly 20,000 nodes to maybe 2,000 nodes as I go from 0 to 20 meters. So it's a huge alteration of the the network organization. The number of links goes from nearly 2,000 links to maybe 35,000 links when I go to 200 meters. So this shows how much the structure of the network is changing. Okay. Here I have the number of components in the system. So as I started, I have 11 isolated components. And then I will increase in whole, and for 65, the system is all connected. So 65 meters is really reasonable to have a completely connected network. So it's not a bad designed system after all, at least in this aspect. So look, we are not considering how many people is walking around. So there is here no dynamical information. And the bus and trains that run in the morning may be different in midday and be different at 11 o'clock p.m. So the system, nothing of this is considered here. It's just maybe an average network. So here you have the maximum degree of the system. As I'm collapsing nodes, the maximum degree of the network increases. So there is a node with almost 800 connections for 200 meters for whole. Okay. All right. So keep this number in mind, 65, because here we have we can say a percolation in the system. With the whole equal to 65, the system is just one network. Okay. This here we have assertivity. Okay. So there is it's well known in the literature that the assertivity for social networks tend to be high. Otherwise, due to hierarchical structure, one expects low assertivity for technological networks. So the public transport network is a social network, or is it a technological network? Clearly, it's a mixture of both, because when you have, for instance, a bus line, there is no hope, but you need to go from one to other. So it's some kind of a technological limitation. But it is also a social option to walk more to connect to the whole network. So we start with a high value, or .75 maybe. And as we increase the radius, the assertivity gets small. So it's approach, in some sense, to a technological network. Okay. So this highlights the role of user displacement in the formation of the functional transport network. On days of heavy rain or heat, the character of the PTN changes. Well, here you have the clustering for the system, and as I collapse the nodes, the cluster increase. So even far beyond the 65 meters, we are still creating greater clusters. Okay. Here we have the average path length, the diameter of the network, and the density of the network. So as I increase the rho, I will have average path, smaller average path length, that is the average distance between two arbitrary nodes. So it's easier to use the network if you have a smaller path length. Okay, the same for diameter. And here the density increases in the sense that because you have more connections in each node. Okay. Here I have what is called a hive plot. And let's understand that. In this X, we have the subway system. In this X, we have the train system. And this X represents the bus system. Each point here is one node, is one bus stop. And the position in the X goes for the connection of the node. The same is true for subway and train. And as I go from rho equals 0 to 65, we have a system that is much more connected. So, for instance, we have the subway nodes. They are strongly connected with bus stops of small connection. This happens, for instance, in Estação Tatuapé or Brás, where you have a strong connection between metro, trains, and buses. So, and you can see the connections among train and subway, as well as train and buses. So, this plot illustrates that aspect, how the system gets really connected when I put this rho parameter. Here the node degrees are normalized for the entire network and not just for the axis. So we can compare here the relative position of the nodes in terms of connectivity. Okay. Then we go to the analysis of degree distribution scaling properties. And here we have 4 scaling diagrams for rho equal 0, 55, 65, 150, and 200 meters. And we don't see much variation here. The axis scales are the same. And the blue dots are the connectiveness, the degree. This is a probability distribution function for the degree of the network. And what we can see, and we can also see the fitting of a power law and the log normal in these 4 plots. And they are nearly the same. It's almost impossible to say if it is a log normal or a power law test. Actually, we did a statistical test for that. And I will not show the details here, but the log normal distribution is slightly, a little bit more better than the power law fitting for this representation, at least. So here there are some words about the fitting of a power law. We used a power law Python package. The package is very versatile, open source tool that facilitates the application of various distribution types of data analysis. The input for this process is just the histogram of K distribution, the degree distribution. So it was observed that the fittings used in both power law and the log normal distributions are nearly indistinguishable. So we made a statistical test, I will not show here, and the log normal distribution was more suitable for the São Paulo PTN. Okay, so I hope now we have some comprehension of the system. And let us look to the robustness of the system. So, as the robustness is an important property in the PTN infrastructure due to the crucial role it plays in the cities. PTN involves the transport of people, and a critical aspect of the operation is to continue connecting people to their destination in face of perturbations. In order to test the robustness of São Paulo PTN, we perform attacks by removing nodes. In practice, such attacks could be caused by power fail, broken vehicles, emergency maintenance, accidents in the roads, vehicles, passengers, road obstruction by several fronts, several origins, natural disaster, and so on. So there is a lot of problems running on this network. So different attack strategies are used to evaluate robustness. We used 3 strategies: random removal of nodes, probabilistic removal of nodes with probability proportional to their degrees, and deterministic removal of nodes from the highest degree to the smaller one. We also perform the analysis of attacks to the links, but here we focus in the attacks to the nodes. Okay, so here we have some simulation. So each of these lines is for a different whole value, so 0, 65, 150, and 200. And in the horizontal axis, we have the number of nodes deleted. First random, then in a probabilistic way, and finally in the deterministic way. So, and what we are showing here is the number of components. So the network gets broken as we attack the nodes. And what we should note here is only that, as expected, that random attacks, that the network is more robust to random attacks. And the worst scenario is when you have deterministic attacks. So we start to feel one component. It can arrive nearly to 300 components as we remove 1,000 nodes. So this is coherent with all you know about random and the deterministic attack in the networks. Okay. Then we studied the giant component against the fraction of removed nodes. So, as indicated in each subplot, rho is 0, 65, 150, and 200. The red points are for random attacks, and the blue points is for deterministic attacks. Yes, that's right. So the size of the giant component decreases as we remove. This is a fraction of nodes removed. So for random attacks, the giant component goes to nearly 0 in a much slower way than the deterministic attacks. And this green line is the percolation threshold predicted by a main field in a random network with the same size of the transport network. So the random network main field prediction is a little bit bigger than the actual transport network. Okay, so I'm approaching the end. Uh, so our conclusions. The group algorithm proved to be effective method to fill missing links. Go obtained with a single component at a radius of 65 meters. This process showed an useful outcome to evaluate mobility public policies, where distance can be used to simulate the user's willingness to move around and access different transport options in relation to the original position. The São Paulo PTN, Public Transport Network, has short average path length in relation to its diameter, has most of its stops poorly connected, and has degree distribution that can be predicted by both power law and log normal. We could not find evidence of scale-free properties on the tested networks, but all of them fall in the small word class, according to statistical tests that I didn't show here. And finally, the Hive plots display strong associativity degree between the PTN subsystems, showing that maybe there is a preference mechanism based on connectivity governing how nodes are linked. Okay. The deterministic attack strategy proved to be more impacting, following by probabilistic and at least random. If fragmentation is considered as a criterion of robustness, the networks with ρ equals 0 showed to be more robust for removal of nodes, because if it already has several components, you don't propagate to the whole network the attack. While networks with ρ 200 showed to be more robust if path length is considered. However, it was clear that the removed links cause significantly less damage, something that I didn't show today, but we performed. One outcome probably related to the multiplicity of links resulted from the grouping process. When I group nodes, I create the number of links gets smaller, but the network gets more connected. Okay, so that's all. Thank you for your attention.
Thanks, Camilo, for your nice talk. We have time for some questions. Okay.
So thank you, Camilo. I think I started having lots of questions during the talk, so maybe we can discuss later. But so I'm gonna ask one more general. Do you see do you plan on having any future directions there, like adding weights to the links if the data allows for that?
Yeah, of course. I mean, just look to the connectivity of the network is the first step. But the people is going from one side to other, and there are limiting the capacity of the links. So we could add here other kind of representations that could allow, for instance, the capacity of the links and the average use against along the day, for instance. So we can also do some kind of dynamics here in the future, eventually. Thank you.
Okay, I wanted to, just to be sure I understand. When you collapse different nodes together, you have one node that represents, for example, you can have one node that represents the station and subway and train and bus at the same time. So, but if you, let's say you have an attack on that node, maybe this is a bit out of the scope of what you did here, but for example, if I have the attacks on the different modes of transportation would be very different. Like if you have a road block, for example, you would turn off all the bus transportation from that node, but the subway and train transportation wouldn't change. But if you have, for example, in Luz Station, you have, if I recall correctly, two subway lines and 3 train lines. If you block the rails on one of them, the others are not affected. So this model of
Doesn't see
attack
that, yeah.
doesn't, yeah.
That-
So do you have maybe an idea on doing different,
Yeah.
because you talked about removing links as well,
Yeah.
which maybe would make more sense in this scenario. I don't know. What do you
Yeah,
think?
look, the way that we use to represent the real network misses this kind of stuff. So when I put together several nodes and I attack that node, in the reality, we may just lose one of the previous nodes, not all of them connected. So this is a clear limitation of the approach. Maybe a better approach would be, as we see several times here this week, to consider multi-layers networks, or even because multi-layers is when one layer goes to another necessarily, but we can have the 3 networks and they can go to each other anytime. So it's a different approach that we see just in previous talk, calculating the eigenvalues and the distribution of that. Well, there are several ways that we can approach this problem to get around of this situation, for instance. Thank you. It's a good question.
Okay, thank you.
Hi, I have a question that, not really a question, but I think an idea that I had back from the first lecture that we had on Monday about cascading. Because I think there's a lot of things in common, right? So a thing that comes to mind is that of redundancy, which is like the last paragraph, right? And I think it's interesting that you mentioned that removing links is less dangerous than removing nodes, because if you remove a node, you remove all of its links, right? So
Yes,
that's much
well,
more dangerous.
well
right?
observed, yeah.
Yeah. So is there a measure of this redundancy of a network? Like if you remove one, how well does it fare afterwards? And also, if there is like a network to which we should like strive for in this whole network, for instance, like a small world network, like is it more robust to these attacks, for instance?
Well, there are a lot of things that can be done. I remember clearly from the Monday talk from Adilson Mota, where he studied the cascade of failures when we strengthen one connection. So nothing of that was studied here, but could well be done. Yeah.
Hi, Camilo.
Hi.
Congratulations for your amazing presentation. Since I'm from the sociology of disaster, let me put one more question. Is like the same question that our colleague put for you? In terms of the types and the time of the attacks, how the instability is incorporated in your model of analysis. Let me put one example, a simple example. A robber could assault a driver in a bus, then they kill the driver.
Wow.
This is very punctual situation, and this specific bus could be retired of the system. But if simultaneously many robbers kill drivers, then the authorities see you have a situation of terrorism attack.
Okay.
So the system, in terms of the strategies, the alternative strategies to reallocate the system of the bus, and the threats for the other public transportation system, we put in the deliberation, and it exiges more time to create alternatives for a city or metropolitan for Sao Paulo. Is your model are considering this kind of set of threats?
No, it isn't. The model is very simple. As I said, it is a kind of the average number of nodes and links along the day, along the week. So we didn't consider some management point of view. That would be what some mayor or public administration would ask. So if I want some grant to to get more work on this, it's better to to answer this kind of things. So of course, yeah. Thank you. Well observed.
Sorry, guys, we are running out of time.
Okay.
We need to, let's thank the speaker again.
Thank you.
Now we're going to have a short talk by Rodrigo Malavasi. I expect that the secretary will go to.
Hello, hello. Rodrigo. Yeah. Hello, everybody. You can hear me, right? So, first of all, thank you very much for the organizer.